Welcome to 5G Technology World. I'm site editor Martin Rowe. There's been a lot of talk in the industry lately about the convergence of 5G and Wi-Fi. But what does that mean for engineers? We know what it might mean in terms of IT people and connecting equipment, but what does it mean for engineers? We have to deal with interference issues, handover issues, all of the low-level details that are needed to make it all work. To find out more about it, we spoke with Fanny Molinarski. Fanny is the Senior Vice President of Wi-Fi products at Spirent Communications. Prior to Spirent acquiring Fanny's company Octoscope, Fanny was president. Fanny, thank you for coming on. Can you tell us a little bit about what this convergence will mean for design engineers?
Excellent question. So we'll start with technology, as you're suggesting. So in fact, wireless technology for both 5G and Wi-Fi actually are converging, and they're one and the same. We're using OFDMA, orthogonal frequency division multiple access. So what it is a modulation scheme and access scheme. And why do we need OFDMA? OFDMA makes the access more efficient for devices that may be sending narrowband traffic like voice, gaming, but they have this wide channel. So we've evolved to have on Wi-Fi, for example, 160 megahertz wide channel. If I'm sending voice over that channel, it takes 1/100th of that. I don't need that channel. I'm wasting my battery. I'm wasting the airlink time. I'm wasting all the time that the access takes, right? Negotiating, collision detection, all that overhead to send one message. So where we are today with machine-to-machine traffic, control traffic, voice traffic, all of that IoT stuff we're doing is we have very inefficient access for these short messages. Now, OFDMA allows us to take tens of these devices and send one frame combined. So we are from frame to frame, we can allocate different sections of the band to multiple devices or one device that wants to stream high definition video, for example. So that is the high efficiency scheme. OFDMA is used in both 5G and LTE as well, and now Wi-Fi. So if you think about it at a technology level, if you are a designer, like you said, Martin, you could design one set of hardware. Now what you have different, obviously, different channel allocations in 5G versus Wi-Fi, different bands, different core software, billing, and so forth. So all of those higher level technologies are different, but the hardware really has converged already. So millimeter wave, as you probably know, requires an array of antenna elements that will work as a phaser to focus the beam. And when you're saying the range we maybe have more range, it's really point-to-point range because we have a focused beam. And we don't have this omni beam where one access point will reach a lot of devices, but we can extend the range. Now, the inherent range of millimeter wave is shorter. Your transmitter power is lower, receiver sensitivity is lower, and you really, the propagation attenuation is higher. So you really, with a single beam antenna element, you don't have the same range. But if you can focus the beam just like you would a flashlight, that's when you get that range. Now, a combination of technologies is powerful because I can be streaming my video over Wi-Fi and projecting it to my display over millimeter wave, for example. So I have more channel capacity there, right? Because they're in parallel. So that's a way to leverage. If let's say your device has 5G, Wi-Fi, millimeter wave, your applications are able to leverage them all and create the high capacity, high efficiency on the Airlink. That's really the win, and the high efficiency comes from dividing the bandwidth.
What about interference? Now, I'm talking I'm talking about radio interference. Because of leakage or anything like that. Have you seen any of those kind of issues come up yet?
With Wi-Fi, it's a big issue because it's so prevalent, right? And especially if you go to the 2.4 band, you have uh, only 80 megahertz or so, and you have overlapping channels. That's a big problem for interference. Why? Because it is possible to set your devices when you go channel, the non-overlapping channels are 1, 6, and 11. If you set to channel 3, you're halfway in channel 1 or halfway in channel 6. And if you do that, there's CSMA-CA, collision avoidance. It disappears because you can't decode half of the channel. It is a very strong source of interference. And you cannot use any of the access schemes to avoid it. And that's a big problem in the 2.4 band. That's why that band is almost useless now. And some of the APs don't even use it anymore. It is a little better in the 5 gigahertz band, but that's where if you start using 160 megahertz wide channels, you also run out of channels. And if you are in a multi-dwelling unit, in apartment building, you will have other users within range that are on the same channels. So CSMA-CA works if, let's say, your neighbor is in range. I can receive his transmissions, and my AP will do collision avoidance and collision detection. I can coexist. But if he's just out of range, then he is a source of noise in my channel. I cannot do collision avoidance with them. So that's a big problem for Wi-Fi. It's a little less for licensed bands like 5G and LTE because they own the spectrum and nobody else is allowed to be there in that spectrum. But for Wi-Fi, it's still an issue.
Are there any interference issues that might come up between 5G and Wi-Fi? Is there any spillover? Have you seen anything like that?
They're very close, right? They're very close because the channel 1 is almost down to 2 gigahertz, right? So yes, I can see that the sidebands will be spilling over and interfering. I'm not intimately familiar with this issue, but I have heard about it.
If you could get that bandwidth into the building and you wouldn't have to switch over to Wi-Fi, do you think that would begin to reduce the usage of Wi-Fi indoors?
That's all up to economics. Of course, technically it will work if you deploy and you have good coverage. But Wi-Fi gives you over a gigahertz of free spectrum today, and it will be increasing. Uh, New bands will be freeing up. Whereas as an operator, you pay several $billions for 20 megahertz of licensed band. So then the question becomes, could you use the same technology and license? So we're living with really outdated technology. When wireless first originated, it was broadcast TV, right? And broadcast TV was regulated into its own slotted channels. One station had one channel, channel 2, channel 4, whatever, they had their own band. They were dumb transmitters. Now we've got sophisticated OFDMA. We don't need to channelize. We don't need to really license these channels and charge billions of dollars, the whole spectrum could be used. And you and I started this interview saying it's really the same of DMA technology. So it really could be all one technology, right? That just dynamically allocates a bandwidth with some sophisticated scheduler that operates between the stations and the infrastructure and the core. And we get the allocation, and it's negotiated, it's requested by the stations, it's negotiated by some central entities, and everything's efficient, and you get charged when you need to be charged. So really, we don't need the FCC. We just need, well, we need the FCC. But the regulations, if they were starting out today, they wouldn't be what they are today. We've inherited them from broadcast TV era. And that's really the problem. But you're asking a good question. And technology-wise, of course, this would make sense, right? It should be one technology, indoors and outdoors. We have enough of the intelligence in it now to make it work really well. But that's not the reality today. The reality is that Wi-Fi costs a lot less because it's unlicensed. And it's not, even though operators are service providers for the most part for our homes for Wi-Fi and the airports now. So they will make a fixed fee. It's still much, much less expensive than 5G or millimeter wave. I would just add also on millimeter wave. So most of 5G is not millimeter wave today. Millimeter wave is a complex, expensive technology. And we design even chambers for it. Cables, connectors, antennas are 2 orders of magnitude the price of sub 7 gigahertz devices. So that's just the reality.
Let's say somebody is building a device for cellular and Wi-Fi connectivity. What kind of things would you suggest that they look into doing to avoid interference between one and the other? And what kind of testing issues come up?
Take medical devices, right?
Okay.
They are a mission critical application. If I'm wearing something like a Lifeline, Philips Lifeline, and I fell, and I will go with that thing from my home outside, and it has multiple radios in it, and it has to seamlessly switch. It has to use whatever interface is available, right? And so there you go. I mean, that's more of a IoT device. I don't know that there's a session that has to stay, for handover. I don't know that. I mean, interference is always an issue, right? You always have to deal with it, mostly on Wi-Fi. And this device would have to figure out how to deal with it on Wi-Fi. And if there's too much interference on Wi-Fi, it has to figure that out and get the call out on LTE or 5G, right? And that's the higher layer intelligence now in our devices that has to kick in for that.
What kind of testing would people have to do? I mean, do you have to have the Wi-Fi, you have to sort of test them independently because of different frequencies or because of different technologies? How's the testing work if you've got both in your device?
Great question. So you need a test system that has all of the bands and interfaces supported. If you're testing a device which is a client, you need to interconnect it in the test system to partner devices like base stations or base station emulators. You test each interface by itself. Usually you would test range and throughput, or throughput versus range. You would sometimes want to test orientation to get the antenna field. So you do that, you break it down, divide and conquer. But then you also want to test the handover speed. So for some of these medical devices we discussed, you want to make some network disappear. Say you put it on connected to Wi-Fi, make Wi-Fi disappear, see how long it takes it to switch over. So then a test system with all of these interfaces present would be really key for that. You also need really sophisticated monitoring. You have to be able to change conditions, introduce interference, introduce multipath, introduce network load in band, for example. and observe some of these scenarios. So for example, some of these handover algorithms, they're pretty sophisticated. You may have multiple interfaces and they're all equally in range, but one of them maybe has a lot of load and the other one doesn't have any load. So that's a decision. How well is this decision made? That's a lot. That's logic that's almost never tested and often doesn't work well. So you need to be able to observe that behavior. You need to be able to set up these complex test scenarios in a test system and observe the behavior of the device. That's the important aspect. So your Octobox system will do that.
Well, thank you very much for your time. And I look forward to speaking with you again.
Well, thank you, Martin. It's always a pleasure. And I look forward to speaking with you as well.